Okay, so we're talking about limits of sequences. This is the definition right at the bottom, the example, followed by definition. We had some numerical analysis as well. Divergent sequences are, that's a good limit. One of the best examples of divergent sequence is alternation between -1 and 1. Another good example of divergence is when n, the whole thing goes to infinity. Convergent sequences look like that green curve on the left, even though we're not talking about curves anymore, but rather points, so like this. So that's why sometimes there is no curve, even if you zoom out very harshly, it is not necessarily create a curve. Okay, so if there is a curve behind it, then you will see a curve when you zoom out and when you have enough points. But when it is an actual sequence, there won't be any specific there won't be necessarily a specific curve. You could end up with like a almost random oscillation or running between, say, like that sine n function. You might remember it runs between -1 and 1 in an almost random manner. Okay, so that is another example of divergence in a most irregular way. Okay, so the definition, as you can see, we're supposed to fit our sequence, or the tail of the sequence. We have to fit it inside of that band. Okay, so when we can do it, okay, then we keep doing it, and if we do it infinitely many times, then we have a limit. Okay, so repeated or rather infinite decimals thought of as limits of sequences of truncated decimals. Okay, and based on that theorem at the bottom. And the last topic is the algebra of limits. Okay, so which is very reminiscent of the same algebra of limits for functions, as well as derivative and so on. They are also limits. So sum rule, quotient rule, and I guess I'll get back to the product rule, but the power rule that then is taken to the next level, and it is now called the composition rule, if you like. Even though the reality is, in fact, that it is pretty much the definition of continuity right here. And to make sure that it is we understand that part, is we might add the statement over here. So what we're saying here, if a function is continuous, then we can evaluate the limit at the bottom by substitution. Okay, so you throw out anything out of the limit. If the function is continuous, then it behaves very nicely with respect to limits, and that is why there is no need to carry out any kind of a limit analysis the way we did last time, but rather you just substitute. Okay, that's what the right hand side says. It says that just substitute. Okay, but let's not forget that it works both ways. So, and vice versa. If the function is continuous, it satisfies this property, and if it satisfies this property, the function is continuous. Okay, so a picture is illustrated on the right. I have a better picture here to make that point one more time. So once again, we're trying to evaluate the limit right here, that's on the left, this one, of a function f at a sequence, evaluated a sequence. What does it mean that f, if a sequence is substituted into a function? We understand it in a way as a composition. So that's what we're seeing here. So the sequence, say xn or a. The sequence that we see is here, so say x1. Let me make it thicker. Say x1, x2, xn, and then the sequence converges to. Can you see it? Vaguely. Oops, that's too big. Okay. No, it's not. Okay. So a sequence, as you can see, is the starting point is a sequence, and the sequence is entirely confined to the x-axis. So in other words, the x-axis of our sequence is the output. If you remember this, this is what we might be talking about. We might put our x-axis vertically, and the n-axis will be our input axis. Okay, so that's what the sequence is. If you want to think about a sequence as a function, then those integer values of n are the inputs. Okay, so these are the inputs are only 1, 2, 3, 4, and so on. Okay, and that gives me the output values on the x-axis. So it is what happens if you want to have both of the axes present and illustrate the whole thing with the by its graph. So that's what you have here. But alternatively, you could save you some dimensions, and this is you can illustrate the whole thing like this. Okay. In other words, you throw out the n-axis and only concentrate on what's happening on the x-axis, and the dynamics is fairly clear. As you can see, x's are progressing towards a, and if that is the case, we say that the limit is a. Okay, so that's what the first picture is supposed to indicate. And now, this is always happening on the x-axis, and now f comes into play, a function f, which is a function of x, and it takes these values of f. All values of x are taken to the y-axis. So two things one thing, the second thing you saw in calculus 1, and now we introduce sequences into this, and then we combine them together. How they combine is what you see in the next picture. As you can see, for every value of x over here, say xn here, what do? We go on like this. We go towards the graph, just as usual, towards the graph. And then from the graph of the function, we go horizontally to find the output value. Okay, so the result is what I'm doing here is f of an. Okay, so it is the function evaluated at the sequence. Okay, so what is the result? The result is, look at the y-axis. What do you see on the y-axis? You see those green circles? What do they form? What does it look like? It's also a sequence, right? Right. So in other words, f turns a sequence on the x-axis into a sequence on the y-axis, and then the question becomes, what if that first sequence on the x-axis converges to a, that red dot over there? Then the question becomes, what about the other one? Okay, and the answer is, yeah, it also converges if the function is continuous. If the function is not continuous, that's not necessarily the case. But the function, as you can see, it is illustrated intentionally. Oh, it looks continuous, right? So and you can see how the accumulation of x's towards a translate into accumulation of y's towards whatever that value is over here. Okay, and you can see the correspondence between x's and y's also produces the correspondence between this a and what is. So if the red dot is a, what's the orange dot? F of a, right? So that's exactly what we're saying here. If we were saying at the composition rule, it is the sequence. This is the sequence I have been talking about. The sequence on the y-axis. Okay, so this is the sequence on the x-axis, a-ans or x-ans. Okay, and well, yeah. So I was using different notation here. So these are a's. Okay, and turns out that the behavior on the such as convergent behavior of a sequence on the x-axis is kind of reflected or transformed into a convergent behavior of y's on the y-axis. Oh, the only question remains is where do they go, and they go towards f of a. If they go towards f of a, we know that this means that the function is continuous. And that is the general rule, is the helpfulness of continuous functions, that they do not require any analysis. We know the function is continuous, which means that its limit is always evaluated one and only one way, by simply substitution. Okay, if the function is not continuous, I can certainly give you a suggestion of if I take the same picture, as this, but also with two sequences, but now what if the function is not continuous? Okay, well this is easy to demonstrate how this plan does not work out anymore. So if I have x is here, y is there, I start the same way. So these are my values of x. So say a1, a2, an, and then at the end I have my point a. Everything is fine. But now let's imagine what if the function is not continuous at this point. What does it mean it's not continuous? For example, we have a gap. We have a jump discontinuity. For example, maybe it behaves like this. Okay, so this is my function y equal f of x. Okay, and then it has a discontinuity. It has a discontinuity at point A, that point that we care about. And as you can see, if now I carry out the same plan as I did there on the right, producing a new sequence, as you can see on all the way on the right. Okay, well that's not good. Okay, so then it doesn't work out, so I go this way. This one gives me a point, and that one gives me a point, and they all behave nicely, giving me a new sequence. I'm building a new sequence on the y-axis. So y1, y2, y3. Okay, so things do accumulate more and more. However, they do not accumulate towards anything that we care about, because this is f of a. And these y's that I have over here, even though they do seem to converge, but they do not converge to f of a. Why not? Because of the gap. That gap over here that I put there on purpose, and that's what separates the value from the limit, and which means that the limit, even though it might exist, it's not equal to what we want it to be equal to, the value. And so you cannot evaluate this limit, say f of an. I cannot evaluate it as by simple substitution because f is not continuous. At x equal a. Okay, so that's the point, once again, to illustrate the importance of continuous functions. Even though continuous functions are not as good as differentiable functions. There is another example, another picture here I want to bring into your attention to, and that is the limits can be illustrated a little bit, and with let me try it. So here it is. I have two sequences. As you can see it all the way on the left. Both of them are convergent. Okay, and then what I did is I took these two planes, well, they don't have specific names, but I put them on two different planes. Okay, one horizontal, one vertical. So once again, the green sequence at the bottom, that's the horizontal plane, and the vertical plane is the red one. Okay, and then you see what I did on the right. What happened on the right, all the way in the right? I build those little rectangles. So based on those two sequences, I used one sequence for the width of those each rectangle, and I used the red one for the height. Okay, so that's where those rectangles came from. But the question now is, what is the pattern that we're seeing on the right? What's happening to those rectangles? Getting smaller. Can you be more specific? In what sense are they smaller? No. What I meant is quantitatively. Quantitatively, what is getting smaller?
The area.
The area. That's right. So as you can see, the width getting smaller and smaller and smaller. That's the green sequence on the left. Okay. The heights also getting smaller and smaller and smaller. That's at the top. Okay, which means that the dimensions of those rectangles on the right are getting smaller and smaller and smaller, which means that the areas are getting smaller and smaller and smaller. So that's what it's supposed to illustrate. And then it is illustrate. What does it illustrate? What does it tell us about sequences? What is the, like it was, so these are areas, okay? And these are the widths, and these are the heights, okay? The heights converge, and the widths converge. And then what we have discovered is the areas also converge. But the areas are equal to the products. They are products of widths and heights. So if we move away from this geometry to algebra, what I was saying.
The limit of the area of the rectangle would be equal to
the area of the product.
Right.
The area of the product will be equal to the product of the limits. Right? So it is the product rule that we certainly remember from Calculus 1. It's just a way to illustrate it and see that it actually makes geometric sense. Because multiplication can be interpreted as literal multiplication of two dimensions of a rectangle producing its area, and then we can see how indeed some kind of a accumulation or convergence of the two dimensions of the rectangles will also produce the same behavior for the areas. Okay, so it is entirely similar to these two properties that I have. So I will just insert it here. Product rule. So the product rule says the same thing, that the product of two convergent sequences is convergent, and the limit of the product is equal to the product of the limits. The formula certainly is very simple, like an goes to A, Bn goes to B, then An times Bn is going towards A times B. So that's the product rule for sequences. So remember that those we always have two notations that we use interchangeably, and either LIM or it is an arrow. Okay, so the LIM is especially common in Calculus 1 for functions, but if you think about it, that's what I used on the right. It is that notation is just as good or even better because it actually matches the geometry. So if you look at that picture on the left, you can actually see these elements, A's, how they are going towards A, and it is almost the notation reflects the reality very, very closely. So that's what I'm saying here. An goes towards A, and that arrow is read that way. Either you say An goes towards A, you say An approaches A, or something like that, and that's exactly what we're seeing here. So it's once again, it's like a process in time that you are getting closer and closer to a particular destination. Okay, even though it takes into the many steps. Okay, so once again, to refresh your memory, so we have the four properties of limits corresponding to the properties of algebra. Algebra of numbers. It's all about sequences of numbers. So whatever you can do with numbers, you can do with sequences of numbers. You just do it element by element. So here you can see how I do it element by element. So I take this one and that one here, and then I multiply them, and I end up with this very first rectangle. Okay, so element by element, so the first elements with first element, second with second, and so on. I'm forming what amounts to a new sequence. So, and then if a sequence is formed that way, we can say something about its limit in terms of the limits of the those two building blocks, whether it is about addition or subtraction, multiplication or division. And the fifth operation is the composition, and it is more complex. But on the other hand, it is if you know the function is continuous, then life is easy. Okay, so the life is easy is illustrated right here. These are the examples of continuous functions that allow you to compute the limit very quickly. Okay, so before we move on to some more complex parts of this topic, let's look at sequences. At some specific sequences that we can study in that without a lot of effort because they are so specific. So examples. It's nice to have a few examples that we can recycle whenever necessary, as well as using them as building blocks. So because these four rules are actually a way to build things, new sequences from old sequences. You just need to have at least a few building blocks so that you can build more and more. So example is, number one is very simple. An is equal to a constant sequence. Okay, so constant sequence. Literally, it is just the same number repeated on and on again, as you can see. So an is equal to n for all n. Okay, so it is very, very simple one, but still you have to be specific and say what is the limit. So limit of a and goes to infinity is equal to a. Well, predictably. Okay, so it doesn't matter what a is. So if the sequence is not changing, then it is that number that is being approached. Number two is the arithmetic progression. The arithmetic progression comes primarily from, well, it comes from, I suppose, maybe motion. So it's either motion when at a constant speed, which means that you over the same period of time you move forward by the same amount, by the same distance. So if you want to go recursively first, so an plus 1 is equal to an previous location. So the next location is the previous location plus, say, plus r. So if my r is the constant, how about I call it the m? Okay, so then once again these are the locations. M is the increment, which is, you can think of it as the speed. If it is really about motion through space, then m is speed, and then so every time you move on and you add m. Okay, so then so that's a recursive, but then it is very easy to write the explicit. explicit formula where an is equal to, it depends on what the starting point is. So the starting point is, say, a naught, okay, and then a naught meaning the 0th entry in the sequence, and then it's followed by the formula of that depends on n. Okay, so if I progress from 0 to n, I have made n steps, right? So the initial location, and this is current after n steps. So if I made n steps, each is the increment of n, m, then how far did I go? N steps. Each step is m units long. Where am I? M steps. I'm sorry, n steps, each m long. N step, each m units. How much did I cover? M times n. Okay, so that is indeed the formula, the explicit formula for my progression. Another interpretation is investment when you contributing a fixed amount of money. Say you put $100 every month, and that how your bank account will be growing. The initial deposit and plus every as long as how many months has passed, multiplied by the amount that you contribute. So 100 will be 100 times 100. After 100 months, you have 10,000. Okay, so there's nothing fancy about it. You can plot the graph like this. You start with a naught right here, a naught, and then you progress at every step. You move a naught like this. So a naught plus m, a naught plus 2m, a naught plus 3m, and so on like that. So it is these points then will be located on a straight line. And that is why I called it m. Why did I call it m? Because usually we use it letter m for the slope. So m is the slope of this line, even though it's not a complete line, it's only made of points, but it's still there's a line behind it like this, and its slope is m. Okay? So these are n's and these are, say, a's. Okay? So what remains is the limit. Okay, so it certainly depends. The answer depends on these two parameters. There are two parameters, a naught and m. So limit a naught plus m n, with n goes to infinity. What are the possibilities? Think about straight lines, and what kind of straight lines do you know? Depending on the slope. On its slope, we can classify all the lines based on their slopes. So at infinity, where are we going to end up if we keep adding elements like this? Infinity, right? So in fact, it is plus infinity if m is larger than 0. It doesn't matter how small an increment we make every time. Eventually, we will end up at infinity as long as that increment is positive. If, however, the increment is negative, what happens?
Goes to negative infinity.
Negative infinity, and the final possibility, m is equal to 0. A0. Right. So this is the answer right here. Okay, the next one's slightly trickier, but let's. So the idea is that of the geometric progression, and the idea is that it still could be about investment, but it is different. It is a compounded interest. So if this is this one is fixed deposit, but repeated. Geometric progression comes from investment which with no deposits other than the initial deposit, and fixed rate, compounded interest. So if the rate is fixed and your initial deposit is A0, so say fixed rate is say R, then how does the sequence progress? How does your bank account grow? Initial deposit of A0. So, for example, how much am I going to have after 1 year? Suppose it is compounded yearly. So R is the interest is yearly interest rate. So how much do I get in the end of the day? In the end of the year? What's that? What?
A naught times 1 plus R.
A naught, 1 plus R, right. 1 plus R. Let me make it capital R here. So in other words, if so after 1 year, so that's A1. So once again, this is recursive. Recursive is A1 is equal to A naught 1 plus R. So if you have 10%, then you multiply by 0.1 every time. I'm sorry, 1.1. R is equal to 10%. That's 10%, which means that, well, if it's 10%, R is equal to 0.1, which means that A1 is equal to A naught times 1.1. Okay? And then A2 is equal to A1 times 1.1, and so on. So that is the compounded interest. It does not require any further investment in order to have your money grow, because whatever you have earned after 1 year, it still becomes your capital part of the deposit, and then that part is also multiplied by 0.1, not only the original amount. Okay, so as you can see, that has happened. A naught multiplied by 1.1, so that 10% that you earned will be once again multiplied by 1.1 after the second year. Okay, so recursive formula then becomes an plus 1 is equal to an, well, let's just say R. So I'll stick with the general situation, because 1 plus, so that we don't have to speak of interest rates necessarily, but we can speak of, in addition, we can speak of things such as, say, population growth. So the R could be 2, for example. If you think about things such as maybe bacteria, and they might double in number every year or every day. Okay, so next day you multiply the previous amount by 2, and then the next day you multiply by 2 more, and by 2 more, by 2 more. Okay, and then you have your geometric progression. Okay, so that is the recursive formula. Now I want the explicit formula. You can guess that if you start with A naught, you keep multiplying by R again and again and again, and then if you have made R steps, from the initial state of A naught, you have multiplied by R n times. So multiplying by R n times, also known as repeated multiplication, is also known as exponent. So it will be r taken to the nth power. Okay, so that's the explicit formula for the geometric progression. So, so once again, you can think about compound interest, and you have this also known as geometric progression as exponential growth, which refers to a bank account or population growth, but it only assumes if your rate is positive. Okay, when the rate is not positive, but rather larger than 1, then rate of the ratio, rather, I would like to refer to R as the ratio, because it is literally the ratio between an plus 1 and an. Okay, so if that R is larger than 1, you multiply by a number that is larger than 1, keep multiplying, it will have growth. Okay, however, you can imagine that population could decline, and you could lose half of the population, say, over a period of time. In that case, you have a decline. Okay, one of the applications you may have seen in Calculus 1 is for radioactive dating, right? Remember that? Radioactive dating or carbon dating. You know what it is? Carbon dating. Yeah. So, the behavior is exact opposite. It's just two examples of exponential exponential function. So either you have exponential growth, or you have exponential decay, which looks like this. So say this is e to the x, and this is e negative x. Okay, and so the behavior is the opposite, but the point where the decay comes from, it is the decaying of certain radioactive elements. And so, for example, if the painting was made with plant-based paint some 100 years ago, then you know how much this particular element has decayed, and it starts decaying when the tree is cut. Okay, so you know by how much it has, by proportionally it has declined, and based on that you can determine how many years ago that tree was cut, when that decay had started. Okay, and based on that you can tell or estimate the age of the painting. Okay, or whether it is painting or something else. They certainly do it with animals, maybe even go millions of years back. Okay, some fossils. Okay, so but that's more complex, but it is really not a calculus problem then, because this kind of business is simply it is an exercise of exponential and logarithmic functions. So if that's how you solve the problem. If you know about that this element decays 50% after 5,000 years, and it has decayed 25%. How long has it been? How long has it been? It decays by 50%. Well, maybe that's an unfair. So if you have only 25% left, while it decays 50% every 5,000 years, how old is it? So 50% in 5,000 years. Okay. I have 25% left, which means how much has it decayed? By how much? So the answer is 10,000, because it takes 2 periods of 5,000 to get to reduce the amount to 25%, which is divided by 2 divided by 2. So 25% is 1/4. So which is 1/2 of 1/2. Okay. So and then that's how you figure out that the answer is 10,000. So that does not require any calculus, even though this understanding of how these functions behave certainly may have come up in calculus 1. The exponential functions, how it is declines, how it is grows or declines, and including things such as how fast it grows in comparison to other functions. So the exponential function grows faster than any other function based, remember that? How that is established? L'Hopital's rule, remember? So the exponential function will beat every polynomial function, even though the power of 100 or 100,000, it doesn't matter, it will eventually surpass it. So that's the thing about exponential functions. Our interest is simpler. We certainly might need to use that information about exponential functions, because we did end up with an exponential function right there. And in order to answer the next question, we're going to need all we know about the exponential function, except it's not base e, but rather base r. So we assume that a naught is not equal to 0, otherwise we do have a constant. So once again, what options do we have when n goes to infinity? What happens to under this exponential growth decay model? So what possibilities do we have?
To infinity.
Positive infinity when we have exponential growth, and exponential growth is guaranteed by what value of r? Greater than 1. If you multiply, you don't want to multiply by 1/2. Okay, so it will cause decay. So it's larger than 1. It is when it is between 0 and 1, then it is like 1/2 as an example. Multiply by 1/2 by 1/2 by 1/2. It will decline towards what? They keep dividing by 2. Where do you end up? What should I put here? What?
0.
0. Okay. What's left is r equal to 1. R equal to 1. An extreme case. What?
It'd be a naught.
That's right, a naught. So there is no change. So it is a constant 1. And then, okay, what if r is less than 0? So these are the 4 cases. And what if it is less than 0?
Negative infinity.
No. Think about it. It's negative. Suppose r, as an example, pick r equal -1. What's going to happen? Multiply by -1, by -1, by -1, by -1. What's happening? It's going to diverge, yeah. So it will oscillate between -1 and 1. So it's not going to infinity or negative infinity. It's literally is going nowhere, figuratively. So as you can see, there's the difference between the top and bottom. Even though both of them can be characterized as divergent, the last one, the first one has some information about it. So you have exponential growth, and you know that growth will approach infinity. However, when you have a -1, there is nothing really happening that is of any interest long term, because it will go up and down, up and down. Because every time you multiply by a number that is negative, it will change the sign, and changing the sign will pretty much make sure that you do not have any convergence. Well, not true. This is only true if it is less than or equal to -1. However, if you take -1/2, what's going to happen? If r is equal to -1/2, if I keep multiplying by negative 1/2, what's going to happen?
It will approach 0.
It will approach 0, right? So even though it oscillates, but remember we actually have that example too. So when you have not only you have the oscillation, but you also have a diminishing swing of the oscillation. So it still converges. So if I have this picture somewhere, well, I guess this is a fair way to describe it. As you can see, it goes up and down, up and down. So you can say that it changes its sign if you do it around 0, and then it just decays towards but because of the swing decays, you have convergence. Okay, so these are the examples. So algebraic properties we just considered, and now the next topic is actually the algebra of infinities and indeterminate expressions. So what is 0 over 0? We just review something that you saw in Calculus 1, and we'll just do it one more time. Yeah, okay, I guess time is up. And think about the questions if you want to know anything about the test.